So in the final part of the lecture, we are going to look at communication that uses channelization methods. So channelization protocols work by allocating a portion of frequency or time. And these protocols can be at a high level characterized into FDMA, TDMA, and CDMA. And each of them allows for an efficient use of resource and minimizes interference that occurs during communication and thus ensures high reliability. So let's start by talking about a mechanism called FDMA, which stands for Frequency Division Multiple Access. So as the name suggests, frequency division multiple access divides transmission into separate frequencies. And each device uses a fixed independent frequency for communication. So the key is that if two devices don't communicate at the same frequency, they will not interfere with each other. And this method is commonly seen, for example, in devices such as walkie-talkie, where a dedicated frequency is used for supporting uplink and downlink communication. Another example is that if we talk about Wi-Fi and Bluetooth devices, their frequency allocation looks to something similar to the figure presented on the slide. And if these devices pick channels which are not overlapping, then they can communicate without interfering with each other. So if two Wi-Fi devices pick channels that are not overlapping, or a Bluetooth and a Wi-Fi device picks channels that are not overlapping, they would not interfere with each other communication. So we are separating them in frequency. And that's the key idea for frequency division multiple access. Next, let's talk about the channelization method that involves allocation of dedicated time slots for communication. And this is called TDMA, or time division multiple access. So this method separates transmission temporarily. So the devices share the same, can share the same frequency channel. That means they're operating on the same frequency channel. But this method or mechanism ensures that their transmission do not occur at the same time, and hence they do not interfere with each other. So how does it work? The time is divided into fixed length windows, and each device is allocated one or more window for communication. So would these windows be allocated uniformly? No, it doesn't have to be. The allocation can be based on some priority, and some devices could be allocated more window or slots for communication to prioritize their traffic over other devices. However, there is a downside to TDMA, and that is that this approach requires periodic synchronization among devices. And consequently, to maintain proper timing, these devices would often need to listen and resynchronize at regular intervals. And performing the synchronization might not be straightforward for IoT devices, which typically have less resources and have energy constraints. So one way to look at a difference between TDMA and FDMA is basically with this graph. So in the case of TDMA, we can allocate all the frequencies to a particular node for a period of time. So a node can have access to all the frequency, but it can only transmit for a period of time. And on the other hand, in the case of an FDMA, the frequencies are divided. So the nodes can use the entire the period of time, but they are only restricted to operate at a certain frequency band. So while TDMA and FDMA has this separation, and some of the earlier systems were exclusively operating on either TDMA or FDMA, but what we find is that in practical systems, TDMA is often combined together with FDMA to come up with a sophisticated medium access control mechanism. And we are going to actually look at some of those in detail in the later part of the course. So let's talk about what are the pros and cons of such static allocation of frequency or time for ensuring multiple access. And this can be understood by comparing them to a set of shared resources. So what are the pros? So it gives you guaranteed availability. So in a way, like reserved seats in a theater, the wireless medium is always available for the allocated users. And this ensures certain level of quality of service. The second is the reduced interference. So as users have their designated resources or time slot, or that means they have their own frequency time slot, there is no interference that occurs during this allocated period. You can think of it as similar that you have a private room in an office, and since each of you have private room, you cannot interfere with each other. So what's the con, or what's the downside of such allocation? It can lead to inefficient resource utilization, because allocating resources statically can lead to underutilization. For example, you have been allocated a fixed number of time slots and you're not using it. for communication. And that means those time slots are left unused and you're not making the best use of the wireless spectrum. And it also has slow adaptability. So static allocation can mean that it is slow to changes in the traffic demand, and this rigidity may result in inability to effectively handle variations in network traffic. So if you have devices coming in or the traffic pattern changes, such static allocations might not be the most optimal way to allocate resource for medium access. So let's now look at something called orthogonal frequency division multiplexing, which builds on some of these concepts. And uh, this modulation scheme is actually used in vast majority of wireless devices that are used today for wireless communication. So frequency division multiplexing and orthogonal frequency division multiplexing are both techniques that are used to send signals over a communication channel. And the main difference are, so we talked about separating in frequency. So in frequency division multiplexing, the entire frequency spectrum is dedicated to carry data from a single source. So for example, when you want to transmit 20 megabits over 20 megahertz spectrum, you are sort of like using the entire frequency band to support communication between a single source and a receiver. However, what happens in OFDM is that the data is divided into many slower bit stream and multiple subcarriers are used for communication. So it means that you have now signal separation. So while FDM uses separate frequency band with which also has sometimes called guard bands to prevent interference, OFDM has these subcarriers which are very closely spaced. But these subcarriers are orthogonal, which means that they don't interfere with each other. So unlike FDM, you don't have guard band and these carriers are much closer, but they are designed or they are placed in a way that they don't interfere with each other. Second is that if you talk about modulation scheme, FDM uses simple modulation scheme, whereas OFDM can employ complex modulation schemes, and each of the subcarrier could be modulated with these complex schemes. In terms of bandwidth efficiency, OFDM is much more bandwidth efficient because of the closed subcarriers. So you don't have this wastage of spectrum for the guard band. OFDM can also be much more multipath resistant because, and also if we just talk about implementation complexity in general, FDM or just sort of like allocating separate frequency with guard band is much simpler than implementing OFDM because OFDM requires typically much more complex processing. So one way to look at it is that in case of OFDM, we could divide the data source into 40 different sources with each with 1 megabits per second. While in FDM, we had one source which was transmitting 40 megabits over 20 megahertz spectrum. So in a nutshell, the presence of guard band orthogonality of the carrier is something that actually distinguishes OFDM from FDM, and we can actually understand this pictorially from this diagram that is presented on the slide. So there is a clear separation between various subcarriers, and these are orthogonals, and they are also sort of like intersecting, as you can see from this diagram. So what are the benefits of OFDM? OFDM offers numerous advantages, especially in fading and multipath rich environment, which is the case actually for most of our indoor environments. So it can be robust to fading. So if OFDM is highly resilient to fading, and this is because of much lower data rate per subcarrier, which and it sort of like allows you to reduce the effect of fading on individual subcarriers. It can be multipath resistance. It's, as we discussed, is much more spectrally efficient because of the closeness of the subcarriers. And it has also adaptability, that it can adapt to various channel conditions because it has these subcarriers and employs more modern or complex modulation schemes. And OFDM has become now, because of all these benefits that it offers, like high data rate, better bandwidth efficiency, resistance to multipath, that it is now part of like modern wireless standards like Wi-Fi, cellular radio, even digital radio and TV broadcasts have started to use OFDM as a modulation scheme. Next, let's talk about another technique that enables sharing of spectrum, and this is called code division multiple access. And it is often used in conjunction with something called spread spectrum techniques. So to understand CDMA, consider this analogy. So if we have several people who wish to communicate simultaneously, in the case of time division multiple access, they would take turn to speak. as the time is divided among them, and then they will talk and when the term comes. In case of frequency division multiple access, they would speak at different pitches that represents different frequency divisions, and that allows them to not interfere with each other. But in the case of CDMA, they would converse in totally different language. And they have distinct code, and that allows you to have simultaneous communication because they're talking in different language so that they don't interfere with each other. So CDMA allows multiple users to share same frequency band by assigning unique code to each of the user signal. And then the signal is spread across wider frequency band, and it can be overlaid by using these spreading techniques. And at the receiver side, the desired signal is extracted using the assigned code. And then you sort of like recover back the information that was transmitted. And what is the advantage of CDMA? That this technique offers increased capacity, resistance to interference, and it also has enhanced privacy when compared to, for example, simple schemes such as TDMA or an FDMA. So CDMA codes can be characterized into two types. They can be synchronous and asynchronous. So let's talk about synchronous first. So the synchronous in this type, it uses an orthogonal codes which exploits some mathematical property which has orthogonality between vectors. So as an example, when the dot product between two vectors is 0, they are considered orthogonal. This property can allow you to have multiple signals to be transmitted simultaneously without any interference, as long as these codes remain orthogonal. Synchronous CDMA is commonly used for downlink communication, let's say from your mobile tower to the mobile phone. And one example of a synchronous CDMA code is something called Walsh code, and it was derived from Walsh matrix. And these are sort of like sequence of binary numbers that exhibits these orthogonality properties. So next, let's talk about asynchronous CDMA. In this type of CDMA mechanism, the codes are not strictly orthogonal and they can be asynchronous. It is typically used for uplink communication, let's say from your mobile phone to the base station. And this type of code can actually accommodate multiple users with varying timing offset, which is a common case in cellular networks. And one example of asynchronous CDMA code is something called pseudo noise sequence, which is also sometimes called gold code. And pseudo noise sequences are generated using specific algorithm, and it has this correlation property which allows them to be used to sort of like perform this translation of data stream using these bits. So we talked about that the CDMA is often used in combination with a technique called spread spectrum. So what is spread spectrum? So spread spectrum is another technique that is often used in conjunction with multiple medium access mechanism. And the primary goal of the spread spectrum, as the name suggests, is to distribute a signal over a broader frequency range. And it results in increased bandwidth. And what's the benefit of doing a spread spectrum? It can make the communication secure, because by spreading the signal over wider frequency range, it becomes more challenging for, let's say, someone who wants to listen for your communication to intercept and decode the transmission. And it can enhance the security of communication channel. Second, it can be resistance to interference and jamming. Because of the wider frequency spread, it is more resistance to interference and intentional jamming, because the impact of noise or the interference on any single frequency component is reduced. Also, it can lead to reduced detection. What does it mean? A signal spread over a wider frequency range has a lower power density, and it makes it more difficult for unauthorized party or the eavesdropper to detect the transmission. So spread spectrum has actually a very long history, dating even much earlier than World Wars, and it was used extensively during World Wars for military applications. And today it has become a part of most of the modern wireless communications, such as CDMA, Wi-Fi, GPS, to enhance security, resilience, and the performance of communication. So we can illustrate this pictorially, how the signal is spread over the frequency in the spread spectrum with this diagram. So in communication systems that employ spreading and despreading technique, the process can be summarized as follows. So we show it also with this general model on the slide. At the transmitter, spreading code is applied to the database. This operation is combined with the modulation scheme. It spreads the signal over broader frequency range, and then the signal or the spread signal is wirelessly transmitted over the communication channel. And the receiver side, the reverse operation is now performed. The same spreading code is used to despread the received signal, and it is effectively recovering the original bits. And after despreading, the demodulation is applied to extract the transmitted information. So next, let's finally look at a technique called frequency hopping, which is also a spread spectrum technique. And in this technique, the signal is transmitted by rapidly switching among different frequency channels sometimes in a pseudo-random sequence. And what's the advantage of you switching the channel, as we show also on the slide, is that it can make these transmissions difficult to detect. So if you don't know the sequence at which your transmitter is changing frequency, an eavesdropper or someone who wants to intercept your communication cannot receive the information because it doesn't know the order in which you are changing your transmit frequency. And to visualize the frequency hop spread spectrum, we can consider two scenarios that are depicted on the slide. First, we can have a fixed frequency allocation. In the first, specific frequency band is allocated for communication. The signal remains in this band throughout the transmission. And then you sort of like change, and this approach is still susceptible to interference, jamming, and detection. But in the frequency hopping, the signal frequency changes with time according to some predetermined scheme. And the receiver would know this predetermined scheme because it allows it to keep track of these changes and receive transmission. And the signal hops between different frequency channels, and it makes it difficult to interfere, jam, or sort of like eavesdrops on the communication. By using frequency hop spread spectrum, a communication system can increase its resistance to interference, enhance security, and reduce very much the likelihood of detection by an eavesdropper. So finally, we will talk about a technique called direct sequence spread spectrum. So this is also something that is very commonly applied in modern wireless standards. And in this method, the signal is multiplied by a pseudo-random code sequence, which increases the bandwidth and spread the signal over a wider frequency range. The receiver uses the same pseudo-random code to recover the original signal. Then, to demonstrate DSS, consider the figure on the slide illustrating the process. So first we have data input, the data bits that are to be transmitted. Then we have a pseudo-random sequence, which is a stream of locally generated pseudo-random sequence that is generated. Then we perform the spreading, where the data bits are combined with the pseudo-random sequence. Typically, we do, let's say, a XOR operation on these bits. This results in transmitted signal being spread on a wider frequency range. Then we transmit the spread signal wirelessly by using one of the modulation scheme. And at the receiver side, the same pseudo-random sequence is now used to despread the signal. So typically, again, if let's say you've applied the XOR operator, you will apply it at the receiving side, and then you will get back the original bits that have to be transmitted. And then you recover, and then you sort of like get back the original bits that were transmitted. So what's the advantage of employing DSS? So because of DSS, a communication system can enhance its security, it can reduce the likelihood of detection, it can increase resistance to interference and jamming, but it can also lead to gains in terms of sensitivity. So it can allow you to communicate at a maybe slightly more communication range compared to without using some of the spreading techniques. So what are the real world protocols and that use these mechanisms? So when we talk about Aloha, which is the simplest protocol that we had seen, Bluetooth advertisements, or for example, long range wireless networks such as Sigfox and LoRaWAN actually use this mechanism for mediating access to the medium. CSMA is very widely used in Wi-Fi, especially the slotted variant. TDMA, or time division multiple access, is used in Bluetooth, but in the connection mode. So when you have established connection between the two devices, you often use TDMA mechanism. It's also used in cellular low power wide area networks such as narrowband IoT and LTE. So if you talk about distributed spread spectrum of frequency hopping, for example, the original Wi-Fi that was introduced in 1997, it actually used frequency hop spread spectrum, and some of the modern standards, including starting from 802.11b, use DSS as a spreading technique. So with this, we come to an end of this lecture.